well enough for computer vision in order to analyze what's going on out there. It's still really an open problem. So that ends our conversation about lightness constancy. As I said, the truth is our computational methods are still not really adequate in this space. It could be it hasn't received enough attention to think of it from recovering each element. It's received actually more attention in the computational photography domain. And I think if you take Professor Irfan Issa's class in computational photography, which I highly recommend, I think you spend a lot of time talking about that there are a lot of algorithms related to computational photography that are connected to computer vision. And this is an area where this lightness and color constancy is an area where we need more work. So the good news is there's plenty of research in computer vision to be done. So hurry up and go get your degree and come join us in the field. Okay, welcome back to Computer Vision. This is going to be our third lesson having to do with essentially how intensity and shape and light interact with one another. In the first one, we talked about the physics in terms of how that interaction works. In the second one, we talked about what if you want to try to recover something about the surface properties of the object, the reflectance function. Basically, you have to make some assumptions about the shape or the illumination. Well, today, we're going to turn it around the other way, and we're going to say, well, how can I recover something about the shape of the object based upon what I'm seeing? So this general area of work was actually started by, I guess, probably Bertolt Horn and maybe some others, but I certainly learned about it from Bertolt way back in the 70s, then continued in the 80s and 90s quite a bit. It's referred to as shape from shading. And the idea is, so over here you see a picture of a real sphere this time, right? And you can tell that this is a sphere, right, with a light source over here. Likewise, you can tell that from this person that probably this is the front part facing you and that the shape tapers off. Likewise, you can tell from the shading here something about the texture and the shape of the face. And the question is how to use shading as sort of a cue for recovering the shape information. So in order to talk about shape from shading, or I'll call it shape from lighting, because one of the things that we're going to do in a little bit called photometric stereo is not so much a shading variation as it is from having multiple light sources. What we have to do is we have to look at the relationship between the intensity that's seen by the camera and the actual shape of the object. Now, that means we have to look at that reflectance function. Remember what we defined, I guess, 2 lessons ago about this interaction between the surface normals and the light direction and the surface itself. And in particular, we're going to introduce a mathematical construct referred to as the reflectance map. And the reflectance map will be the basis of a lot of what we'll do today. So necessarily, we have to introduce a little bit of notation in mathematics in order to make it easier to understand what this reflectance map is. So we're going to start by assuming we have a surface Z of x, y, right? So here we have Z in this direction, x and y in that direction, and you have some surface. As you move in, say, the x direction and the y direction, your z value changes. And in fact, you can talk about how z changes as you move in x and y. That would be the partial derivatives of z with respect to x and respect to y. And we're going to define 2 variables referred to as p and q to represent these derivatives. Now, there's a little bit of ambiguity in the literature. When I learned it from Bertolt, p was the partial of z with respect to x. Q is the partial of z with respect to y. As I was rummaging around the web to see how people talk about this, all of a sudden sometimes people use the negative of the partial of z with respect to x and the partial of z with respect to y. And it turns out when you do it as the negative, it makes some formulations a little bit easier. So I'm going to use it as the negative, but you can use it either way as long as you're consistent. So let's assume we have some sort of a surface normal. Okay, so here we have our surface normal drawn, and it is on a surface. Okay. If we have a point on a surface, we can define 2 tangents, all right? One is, if I take a step just in the x direction, there's a question of how does z change. So if I step in the x direction, no change in y, then my change in z will just be the partial of z with respect to x, and so that's negative p. So tangent in the x direction, so it's on the surface. Let's draw ourselves a little surface here, put a point here, and this is one tangent vector. Okay? Well, the other tangent vector we can have is if we just take a step headed in the y direction, then there's how the z changes as a function of y, and that's negative q, and so that would be another tangent. So if I want to find the surface normal, that's easy to do. I just take the cross product of those 2 directions. By the way, these vectors, I haven't made them unit vectors or anything. They're just taking a step that goes 1 in the x direction and changes however much it does in z. Same thing for the y. So if I want a unit normal, what I have to do is I have to take tx cross ty. So I remember the cross product of two vectors is perpendicular to that, right? So I take tx cross ty, and if I want it to be a unit vector, I have to normalize it by the magnitude, okay? And so when you take tx cross ty, you get pq1, and the magnitude of that, of course, is the square root of p squared plus q squared plus 1. By the way, so the reason I use the minus partial respect to z respect to x and y is that allows my normal to be pq1. If I did it the other way, it would be minus p minus q1. So it's the same difference. So that's the algebraic description of P and Q, and that's important because we're going to use it. But it's also important to understand the geometric interpretation, because when we reason about multiple constraints, it'll be easier to think about that. To do that, I have to introduce something called the Gaussian sphere. So here we have a sphere, and the idea of a Gaussian sphere is it represents all possible surface normals. So suppose I have a shape, and I'll just draw some sort of shape here like that. It's kind of a potato-looking thing, right? If I have some point here, it has a surface normal in some direction. Well, that surface normal is right here on the sphere. And likewise, if I had a normal here, that one would be right there on the sphere, okay? So there's a mapping from all the surface normals to the Gaussian sphere. And in particular, if I have z as a function of x, y, and I'm only worrying about things pointing up, then essentially only the top half of that sphere do I have to worry about, right? So there's going to be a relationship between every normal and a point on the Gaussian sphere. So the PQ space that I was just talking about is actually a projection of the Gaussian sphere. And the way it works is as follows. Imagine, and I'll draw this in 3D in a minute, but here's in 2D. Imagine I have an origin at the center of the sphere, and I come out at the location of that normal, and I hit a plane that's located at the top pole of the sphere. So here I'm showing it in 2D, just makes it a little bit easier, but actually to look at PQ space, we have to look at this in 3D. So here the idea is, here's my little normal, it was there, and it points up until it hits this plane, and that location would be P0, Q0. All right, for this particular normal. And this z equals 1 plane up here, that's sometimes called the gradient space or the PQ plane projection. And the idea is that every normal has a PQ value. So I can represent normals just by their PQ value. And so now we're going to use that to define our reflectance map. Got it? Cool. Let's suppose I have two vectors. So I'm working from a point. I've got two vectors. I've got a vector S that's in the direction of my source, and a vector N that's in the direction of the normal of the surface. All right. Well, those vectors are whatever they are. Their unit vectors are sort of small s, small n. So remember, I can project any vector up onto the PQ plane, and that's what this is. This is at the z equal 1 PQ plane. So I've got a PQ for the normal of the surface, and I've got like P sub s, Q sub s for the vector that is in the direction of the light source. So when I write that, I get the following, right? Remember we said that our unit vector n is just PQ1 divided by the magnitude of P squared plus Q squared plus 1 square root of, and likewise the unit vector in the direction of the source is just PSQS1 divided by its magnitude. All right? So far, so good. So we have an algebraic representation of both of those normals. So let's suppose for a moment we have a Lambertian surface. Then the only thing that determines, in terms of the geometry here, the amount of brightness that we see is just this angle I, which is kind of lost in this mess here. But there it is. It's the angle between those two vectors. And what I need to know, of course, is the cosine of that angle, right? That's the Lambertian surface equation. Well, given all of this algebra, we can represent that cosine as follows, right? The cosine of that angle is just the dot product of those two unit normals. So it's the dot product of n, dot product of s, which is the dot product of these quantities, which is written right there. Okay? So that is the representation in PQ space of what that cosine of that angle is. So now we're ready to talk in general about the problem of shape from shading. So the basic problem is this. Given, say, one, maybe more, but for now one image that looks like either this top image or the bottom image, can you, the computer, recover for me a function z of xy? So that's why it's going to map onto this gradient space nicely. So we're imagining that we've just got a single viewpoint. You can think of z as coming towards me, and I want to know the height of the function as I go over the image. By the way, this is just one representation of depth. It's a very viewpoint-specific representation of depth. If I had multiple cameras and I had different viewpoints, then the notion of z as a function of xy would not be a great representation of the geometry that's out there. And in fact, much later in the class, we'll talk about other depth sensors and things like point clouds, which is a different way of representing geometry. But for here, we're just talking about z as a function of xy. So the fundamental question is, given this single image, can we recover the 3D shape? Well, as we talked about when we did lightness, fundamentally this is an ill-posed problem, right? Because I don't know what the underlying albedo is, and I don't maybe not know what the illumination is. So there could be lots of different shapes and combinations of illumination, albedo, that would give the same image. So, as I said, this is ill-posed. In order to solve this, we have to make some form of assumptions. And those assumptions can be the lighting is known, so I know the direction of the light. Maybe I'm assuming that it's Lambertian and that it's the same albedo everywhere. That would be an example. Or maybe I say that I know what the boundary conditions are. What we're going to have to do is we're going to have to bring in some other kinds of assumptions to make this work. So what we're going to do is, in order to figure out how to go from an image to the shape, we're going to talk about this reflectance map. So the reflectance map relates the brightness I of xy. And again, I'm just going to talk about sort of the brightness in the image, assuming that the image is linear with respect to the light that's hitting it. So I'm not going to talk more about radiance or irradiance, etc. I'm just talking about the lightness or the brightness of the image. All right. So the reflectance map relates the image brightness to the surface orientation, remember PQ, for a given source direction and a given surface reflectance. Okay, so this assumes, for the moment, that you know the source direction and you know the surface reflectance. Let's first consider the Lambertian case, all right? So here we have our same math again. We're going to assume that we've got some source brightness, which we'll just call K here. We have some surface albedo, rho. And we're just going to use our same equation as we had before, that rho times K times the cosine of the incident angle, right? That's the angle between the source and the normal, is what's going to determine how bright our image is. And what we're going to do for the next little bit is we're going to assume that just rho times K equals 1. Or another way of saying it is we're just going to assume that our image intensity is the cosine of the angle. You could make it proportional to the cosine of the angle, but the idea is that it's a fixed number. In fact, later we are going to assume that it's proportional. Clearly what matters in the brightness that we see is this angle, the incident angle between the normal and the light source. All right, so here is the mathematics of our Lambertian system. And in order to try to keep everything straight, I've sort of color-coded. The normal is pinkish, purplish, magenta. Is that fuchsia? Yeah, I don't know. I don't really know my colors. And this sickly green, bluish, I don't know, some color. So we got sickly purple and sickly green, but just keep them straight, all right? But the idea is the purple is the surface normal, the green is the direction towards the illuminant. So the dot product that we showed before is just P times PS plus Q times QS plus 1 over the normalization. And we refer to that as R of PQ. And this is the reflectance map in this Lambertian case. Okay, so this R of PQ. So what is that going to look like in PQ space? Well, to figure that out, we can actually just do it algebraically, but it's actually kind of cooler to do it geometrically. All right. So here we have our light source, and we have some vector pointing up to our light source. Now, if my normal is some theta I away from it, that means that it is in some cone around